In this set of notes, we're going to look more at the properties of derivatives. So the first thing is when interpreting a derivative, we can interpret a derivative in context of different applications, and section 4.2.1 of your book looks at those interpretations for velocity, population growth, and rate of a chemical reaction. Now these are not the only applications that are out there, but they are three common ones, and so I'll leave you to read that section on your own. And again, it's just about the application and interpretation of derivative in context of those applications. What we're going to primarily focus on in this video is differentiability and continuity. And so recall from from our previous section, we have this definition of a derivative. So the definition of the derivative does involve a limit. And notice that part of that definition is that we do require that the limit exist. And looking at the limit itself, notice that that limit does have to exist coming from both the right and the left. And so for this reason, knowing about limits and continuity is very important. And so we stated previously that the limit may not always be defined. And so generally we can use those methods from chapter 3 to determine if the limit does or does not exist. And we can also use the geometric interpretation of the derivative. In other words, the derivative gives the slope of the tangent line at a specified point to help determine if that limit or the derivative exist. And so we're going to look at two examples. Your book has some other examples as well. But often it's useful to look at a plot of different functions to kind of get an intuitive feel for whether or not the derivative is going to exist. So we'll start with this one first. So here we have f of x is equal to the absolute value of x plus 2 minus 1. And so anytime you see a function with an absolute value in it, it's often useful to write that as a stepwise or a piecewise function. So let's start by doing that. And so if we look here, we can see that since we have an absolute value, we know that sometimes inside the absolute value that quantity is going to be negative and sometimes it's going to be positive, and then the absolute value is going to make that positive. So often if you're trying to figure out how to write that as a stepwise or piecewise function, it's useful to start out with a number line, and so that's what I'm going to do here. So I'm just going to draw myself a number line. Now looking at the piece inside of the absolute value, I can see that when x is equal to -2, I would have a 0. So anything greater than -2 is going to produce a positive value inside the absolute value, and anything less than -2 is going to produce a negative value. And so what that tells me is when I consider that piecewise function, -2 is really where I'm going to break that into the two pieces. So drawing out my number line. And again, this is really just to help me, kind of visualize what these values are going to look like. So what we're going to do here is we are going to consider when x is greater than or equal to -2 and when x is less than -2. Now the choice of where to put the equal sign, I could have put it with either of these. Either choice would be perfectly fine. I think your book, it looks like your book tends to put the equal sign with the greater than symbol, but again, you can only have it with one of them, but it doesn't really matter which one that it's with. So if I'm going to consider these two cases in order to write my piecewise function, I know I'm going to have two cases. I'm going to have when x is greater than or equal to -2, and then I'm going to have when x is less than -2. So again, coming up here to my number line, I'm considering this piece, and then I'm considering the piece to the left. Now to help me visualize that, one way that we can do this is I could draw a closed circle line that goes to the right, and then I have an open circle line that goes to the left. Alright, so now I need to figure out what does f of x look like in these two cases. Well, notice that whenever x is greater than or equal to -2, I'm either going to have a 0 or a positive value inside of the absolute value. So just kind of writing myself a note up here. When x is greater than or equal to -2, I know that I'm going to end up with x plus 2 will always be positive, so I can actually drop the absolute value, -1, and that's going to be equal to x minus 1, x plus 1. And so in the first case, I'll have x plus 1. Now, in the second case, when x is less than -2, I know that whatever value is inside of the absolute value would end up being negative. And so here, what I would end up with is x plus 2, but this would be negative -1. And so I would have minus x minus 3. And it's always a good idea just to kind of spot check to make sure that the f of x specified here with the absolute value and the f of x specified with the piecewise function produce the same values. And so again, it's not a formal proof, but I like to spot check a couple values. So for example, let's let x be equal to 10. So when x is equal to 10, we have the absolute value of 10 plus 2 minus 1. Well, that's going to be equal to 11. And then looking at the piecewise function, here we have if x is equal to 10, it's greater than or equal to -2. So we would have x plus 1, which is equal to 10 plus 1, which is equal to 11. And then let's also check when x is equal to -10. So when x is equal to -10, using the first function, we have the absolute value of -10 plus 2 minus 1. Well, -10 plus 2 is going to be -8. And we take the absolute value of that, and that is going to be 8, minus 1 is 7. And then if we look at the piecewise function, -10 is less than -2, so we would have negative times -10 minus 3. Well, -10 or minus -10 is going to be positive 10, minus 3 is 7. So our spot check checks out. All right. So the reason it's useful to write these as a piecewise function is that can often help us determine where we may have an issue with continuity or we may have an issue with the limit. And so we can see that if we're going to have any issues, these are probably going to occur at -2. So let's just kind of draw a vertical line at -2 on our graph. Okay, so here is -2 on the graph. But I didn't mean to change my thickness there, so there we go. So there's -2, so that's where we know that we might have some issues. And we do see, looking at the plot of this function, we do see this really sharp point, and we could call that a corner point on the function where we might have a potential problem. So next, let's talk about in terms of the derivative. The derivative we've seen is really defined by a limit. So let's kind of talk about what's happening here. So first of all, we could consider the t, because that's the point at which we're interested, to be equal to -2. And then remember that we're going to look at a distance h above and below there. So here, and remember h is arbitrary, but this would be equal to -2 plus h. And then we could have a point down here. That would be -2 minus h. And remember, the limit that we're really concerned about is we're interested in the slope of the tangent line as this distance approaches 0 from either side as we move towards t equals -2. Well, notice for this particular line, here we have the slope is equal to 1. And on the other side, we have that the slope is equal to -1. Now here, since we have a linear line, we know that our tangent line is going to fall directly on that line. So notice as we move from the right, as we close that distance from -2 plus h to t equals -2, the slope of that tangent line is going to approach 1. Whereas from the left, as we close that distance between -2 minus h and a -2, that slope is going to approach -1. So our limit as we move from the right to the left is not equal to one another. We do have different slopes. And so for that reason, as we close in on that distance, when we have this sharp corner point, we're not going to have, that limit exist. It exists from the right and it exists from the left, but they're not equal to one another. So for that reason, what happens is when you have these sharp points in a plot, it's not going to be differentiable at that point. So here the function is not differentiable at -2, but it is continuous at -2. And so this is an example where you can have a function that's continuous but not differentiable. And so there's a theorem in your book that says if a function is differentiable at a point, then it is also continuous. But the opposite is not true. We can have continuous functions that are not differentiable, and this is actually an example of one of those. Now, the reason that that sharp point is so important is if I kind of just draw over here, off to the side, imagine if instead of a sharp point, I had something like this. Well, notice when we don't have that sharp point, in this case, let's say we were interested in moving towards this direction, as we move towards the right and the left, as we close that distance between t and h, so there's my t plus h and t minus h, as we close this distance, we don't have that sharp point. So in that limit, we are actually going to find that that slope of the tangent line, we are going to actually be able to find that here. And it ends up, as we've seen previously, recall that the tangent line in a case like this actually looks something like this. And so that's why that sharp point can be such an issue. All right, so let's look at another graph. So here's another graph. So here f of x is equal to x minus 1 divided by x plus 1. And here's what that graph looks like. And so notice here, if we look at -1, or x is equal to -1, so this point, kind of roughly draw on here, we can see that we're going to end up with a similar issue. If we're looking at the slope of the secant line, or the tangent line rather, as we approach from the left and to the right, obviously we're not going to converge to the same spot. And so for that reason, this is another example where if we were interested at taking the derivative when x is equal to -2, we wouldn't be able to do that. We have an asymptote. We can see that, from the right, this function is going down to -infinity. And from the left, it's going up to +infinity. So if we were going to try to draw a tangent line where x is equal to -2, it would be impossible to do that. And so this is another case, just by looking at a graph, we can kind of say, okay, this function is not going to be differentiable at x is equal to -2. Now, that's not to say at other points we couldn't take the derivative. So for example, suppose we wanted to take the derivative of x equals 10. At x equals 10, we would be perfectly fine. We could definitely, consider a point t. We could look at t minus h. Up here we would have t plus h. We could consider, looking at that secant line. We could also look at the tangent line. And we could very easily take the derivative in this part of the function. And so this is really, we need to consider when we're taking that derivative, we are considering it at a single point, whether or not that limit exists. And so we can see in this case, when x is equal to -2, we're not going to have that. And so your homework for this particular section, what I'm going to have you do is, in your textbook, there are several problems that are very similar to these where you're going to look at different graphs and see if you can find a point on that graph where we might have a problem with taking the derivative. And so as usual, when we make plots, I recommend making those plots in Desmos, and this will hopefully help build that intuition when we're thinking about what plots look like and whether or not, the function at certain points is going to be differentiable.